right. Welcome to the stream, everybody. Hope you're having a great week. We're getting things rolling here. This will be an open stream, so if you have any questions or anything you want to put out there, chiller related, including hydronics, if it's involved in a chiller plant, cooling towers, things of that nature, let's talk about it. I'm trying my best to answer the questions as best I can. This will continue to be a weekly series, and so I'm very excited. This has gone really well so far. Y'all have responded very well to it, and so I'm happy to try to be here and just help as much as possible, right? That is the whole purpose and the goal of what we're trying to do here, is provide help and answer the questions that you may have a hard time getting an answer to. That is something that we struggle with as a trade, and the ability to trickle down knowledge and information and actually helping young technicians come up, grow up in the trade, and getting the correct answers that they need. Some of these concepts, especially with the hailstorm of information that is online at this point, it is actually quite easy to get the wrong answers, or maybe answers that are used in different context. And that's something that is dangerous, because a lot of the material I see out there when you try to go do some research on something, it's very much, say, engineer level type stuff, or it's something other than a chiller technician. And that context can be very misleading in the end, and it could take you down some pretty, say, unfortunate roads, or lead you to believe that things operate in a way that may be a bit outside of what's actually happening, which then influences your ability to troubleshoot, stuff like that. So one of my goals here is I want to help answer these questions in our context. What does this mean to us as chiller techs? Not as an engineer, not as a customer, facilities. What does it mean to us? So that is my ultimate goal. So if you have any questions at all, go ahead, get them in the chat, and we will get to them. So today, let's start off with our first one here. Hard time understanding how a higher DP means more GPM. If you slow the water flow through the heat exchanger, the leaving water would have more time to absorb heat, resulting in a lower leaving water temperature. So we do have to be careful that we're not confusing DP for differential pressure and TD for differential temperature, okay, or temperature differential, pressure differential. Be cautious of that, all right? And there's a lot of acronyms. That's one of the things that we need to be very mindful of. That's one of the resources I've considered making. I just haven't got around to making, is an actual acronym breakout of what all of these things mean, and like a short blurb or definition for each one, because there's just a bunch of them. Like, we deal with a lot of just little acronyms. Anyway, so in terms of TD, temperature difference, if we slow down the GPM, or lower the GPM, then yes, we will end up having a higher TD, because we can pull heat out of the water easier, which makes it easier to hit leaving water set point, and it's something we have to be careful with. And I do just want to hit on this again, that there is a difference. So getting back to the pressure side of this, there is a difference between how we rate a heat exchanger and how we rate, say, a valve, or like a balancing valve. So with a valve, if we create a pressure differential across there, or a strainer is another example of this, the more differential across that component, the less flow that component is actually letting through it. Whereas with a heat exchanger, if we want more flow, we're trying to increase the differential. Now, more flow does reduce the temperature difference across there. So to your point, yes, if we are lowering GPM, we will make leaving water set point, or we will get colder leaving water easier. And if we're raising GPM, it will be harder to achieve that. And the goal is to hit the correct, call it sweet spot, if you will, the design point in the middle there. Because that is a symptom that we can have. We can, in some cases, force so much flow if a plant's that badly designed, and like I've come across them. So we can force so much flow through the heat exchanger that ramping that compressor as much as we can't make set point properly, or we're pushing the compressor way past where we should to get there. And so I've had that where you start having these crazy approach values, and it's because we're trying to overstage the compressor in order to get the water temperature down, because we have so little contact time. So the water's moving so fast, we have with such a high GPM through the heat exchanger that we don't have enough contact time, and it ends up forcing the compressor to stage up higher, which ultimately will force our saturations to drop lower, which gives us a higher approach, the difference between leaving water temperature and refrigerant saturation, specifically evaporator approach in this case. So because we have that higher approach, we're allowing a higher rate of transfer, right? So the bigger the gap, the faster it's going to flow from water to refrigerant in terms of heat, just to achieve leaving water set point. So that would be a high GPM flow, which is not good, because then we're just putting way more stress on the machine. That's going to put more stress on our tube bundles, the whole bit. So when we are running a low GPM, something we have to be mindful of is we could have a really good temperature difference, or TD, across our heat exchanger. So the entering water and leaving water, maybe we've got a 10 degree and we're at that 10 degree mark. Keep that in mind. But because we don't have enough GPM, we're not actually moving that much heat. So our chiller is not staging up that much. What that will also mean, though, is that the whole space, whatever we're cooling, if it's comfort cooling, the building space will begin to get uncomfortable for the tenants. If it is a manufacturing process, we're going to struggle keeping up with the manufacturing equipment. Eventually, that entering water side is going to start to rise and increase, and we'll have even higher and higher and higher temperature differences, even though we're technically at design conditions in terms of temperature difference at the chiller. And that could be a symptom of low GPM. So if we're not moving enough flow through the heat exchanger and we're not creating enough differential pressure, then that will end up having we'll hit set point even though we're not actually moving that much heat, just because there is so much contact time with that water. We're able to just draw the heat out of it more than we're actually flowing water through it. Hopefully, I'm hoping my phrasing there is helping kind of bring some clarity to this, and just the fact that we have DP for GPM and actual in temperature difference, that there's a separation between those two. They're not the same. Let's see, do I want to hit anything else on that topic? Higher DP means more GPM. If you slow the water through the heat exchanger, the leaving water will have more time to absorb heat. Yeah, no, I think it's good. The big core concept there is getting a grasp that higher differential across the heat exchanger, evaporator, condenser, either or, does mean a higher GPM. And that will influence our temperature differential. Those do have a correlation, because how fast the water moves does impact how fat or how much approach is needed to achieve the rate of heat exchange that we need to be successful. Anyway, how you doing, everybody? I see we got plenty kind of jumping in. If you have any questions, feel free to get those in. I've got a bank of questions today I'm going through, but if you have one in the chat, I'll be able to get to it very, very quickly. And I will prioritize the chat questions over the, say, bank of reserve questions, just to make sure that whoever's here is getting their questions answered. And if we need to add additional context or discuss it a little bit further, I can help do that. I hope you are having a wonderful week and a wonderful weekend. How to handle in humidity. So, Zara, if I say that right, how to handle it. So, handle what in humidity? So that's give me a little more context in that, because I could go quite a few directions. Give me a little more context, if you will. Because we could go, how to handle what? Cooling tower approach with humidity and managing cooling tower temperatures. We could go space, relative humidity for comfort, right? And what we're doing with the chill water system to try to help achieve that. Like, I could go quite a few directions with that. Chiller. So how to handle humidity chiller. Let's see. Sorry, I'm trying my best to understand your question, because I want to answer it correct, in a useful way. I don't want to just throw a bunch of random information out there. How to handle. So on the chiller side, so you're asking if we've got a humidity issue and we've got a chill water loop, what do we do? Does that sound about right? So from the chill water perspective, which, chiller. So from the chill water perspective, what do we do when we're having humidity problems? And then, at that point, are we having high humidity, low humidity? Most of the time we're dealing with a high humidity, I would say, is the most common struggle. So if I'm on the right track with that, just let me know, and I can run with that to a degree. How you doing, Froggy? I see you in the chat, buddy. Yeah, if anybody has any questions, get them in. Like I said, I do have a bank of reserve questions. How to handle in humidity on chiller. Handle in humidity on chiller. Well, the chiller itself doesn't do handling. Okay. All right. I think I understand your question. Okay. Let me see. Let me take a crack at this and see what I got. All right. How to handling in humidity on chiller. So one of the things I want to clarify with this is, think of why do we try to go for a 45 degree for comfort cooling, as an example, for chill water? Like, why do we shoot for those mid 40 temperatures to begin with? Well, it comes back to trying to achieve dehumidification, right? So technically, if all we were worried about was sensible load, and we just need to achieve a certain air temperature, we could run higher chill water temperatures, and we could achieve a temperature set point. We can hit 70 degrees with higher chill water temperatures than in the mid 40s. And we could probably do so and be far more energy efficient, because all we're doing is hitting the sensible set point. if we're not taking latent heat or humidity into account. So the whole purpose of those mid 40s is so that we can achieve a cold enough coil to allow for proper latent heat intake. The same reasons why we run in the mid to low 40s with RTUs and split systems and everything else in our trade that operates within that saturation band. That is the purpose that we're trying to achieve. It is about humidity control. Now, you could go either way. So let's say, and we're just focusing on comfort here because now we could get into data centers and how they control and stuff, and all this will kind of play a part. So yeah, we can run with this. If your median set point is 45 degrees on the chill water set point, but you're struggling to meet humidity requirements, whether it be comfort cooling space, whether it be a data center, either way, where you've got a server rack and we have very critical humidity control in there. And if you're not familiar, it is very common to use chill water coils in data centers. You know, many of these, especially smaller ones, I would say I see are refrigerated based coils, or we're flowing, they're DX based, right? We've got actual refrigerant in the coil. But a lot of your larger ones, in my experience, they're going to be chill water based. You're going to have a whole bank of chillers and reserves. Like, it's a whole thing, data center life. But anyway, humidity is critical. So if our airflow aspect on the space is correct, and we're actually flowing air, we're making static pressure, we have our CFM through the coil that we need to, and we've already gone through the extent of, say, lowering CFM a little bit to try to allow more dehumidification in the space, because that's part of it. If we can slow the air down on the coil, then we can better achieve better dehumidification, which, you know, it's this exact same principles. Even though it's water in the coil, all the other principles we have are still the same. You know, that 45 degree water is no different than trying to achieve a 45 degree saturation temperature if it was a DX coil with a refrigerant inside. Like, all of those principles still completely line up and match up step for step. We just exchange refrigerant for water, and instead of having a saturation process happening inside of the coil, we're just allowing that water to absorb the heat, and water is actually pretty freaking fantastic at doing that, by the way. So yeah, you've taken steps to account for the air side of this. So the airflow itself, you've gone through those steps. All right. A simple step next would be lower the chill water set point. And this is a very effective, and it doesn't take much, but it's a very effective way to really help, because this is one difference from say a DX refrigerated system to a chill water system. With a DX system, so let's go with RTU, okay? When we lower airflow or lower CFM through the coil to try to better dehumidify, well, something else is also happening. More than just slowing the air down, most of the time our saturation is also dropping with it a little bit, and the two operate in conjunction with each other. So it doesn't take a huge adjustment to get a lot of benefit from the dehumidification side. And this is slightly different with chill water, because lowering airflow, lowering the CFM, doesn't lower your saturated coil temperature, which in our case, 45 degrees set point. So those don't track the same way. And what we end up having to do is, you can just lower that set point a little bit at the chiller. So 45 is your standard. Go to 43 or 42. You know, don't get too crazy with the adjustments. It's not going to take a whole lot. A little bit of an adjustment, a couple of degrees at a time, will make a huge difference in how much more latent heat that coil is able to take in. And the colder we can get that coil, the more we can transition the ratio to where we're taking in more latent and less sensible to help with that dehumidification process. Because yes, water, if we've got a coil designed for a 10-degree split across it in terms of 45 in, 55 out, right? If that's our base design, then there's only so many BTUs of there to be taken in per gallon of water that goes through there. But by lowering the temperature of the water, we're able to take in more of the heat, more of the latent heat. I'm sorry, the humidity. We're able to take in more of the humidity into the coil. So by taking in more of that humidity and having a more latent heavy ratio, by having a colder coil, we can better dehumidify. And this is also true and vice versa. If you're struggling with running a really low humidity and you need to keep more humidity in your space, then raising that coil temperature, that will help. Again, this exact same concepts and theories to a RTU. If we are struggling with over dehumidification, we're pulling too much humidity out, you can speed your fan up, and it will take, at that point you'll start processing more sensible heat, less latent heat, but again, your saturation temperature will typically increase in conjunction with the CFM increasing across the coil. The water temperature is not going to, the saturated, water temp, if just hopefully you're tracking with the analogy here, but it's not going to track the same way a DX coil would. So that just means that we manually raise that set point at the chiller itself. And by doing so, by getting a little bit of a warmer coil, we're not going to take in as much humidity, as much latent heat, and you'll be able to maintain a better humidity in the space. And so then you just have to, depending on what your problem is, you can adjust either direction to achieve what you're looking for, so that you can make better set point, because it's not always just an airflow issue on these systems. If you're having humidity problems and such, it's not just an airflow problem all the time. Now, many times it is. In my experience, most of the time, you adjust the airflow settings and you get the air distribution in the space correct, most of those humidity problems will kind of peter out. But sometimes it's just not always true. And so that's where adjusting that set point can be useful. Now, something that a lot of people are going to throw out there is make sure you're at design temp, engineer, design. Yes, this is true. If you have that data available to you. There's lots of times we don't have that. We don't have the original schematics, or in my case, I sometimes had the engineered drawings, but they were, 5 retrofits ago. There were 5 build outs with different tenants and different configurations, and what they had versus what I've got now are just not the same thing. So we then have to take our experience, take our base foundation, and apply it from there. And I do want to clarify, just in case this is not fully understood. In terms of humidity at the chiller itself, humidity will impact a water-cooled system if it has a cooling tower. So we're talking ambient outside humidity at this point, because a cooling tower's ability to control leaving water temperature out of the tower is based off of the wet bulb temperature. So the more humidity we have outside, the higher our wet bulb is going to be, the more our cooling tower is going to struggle. So you'll have to take that into account, and that's how humidity can affect a water-cooled system. An air-cooled system has no effect. So condenser coils on an air-cooled are strictly rejecting sensible heat. So even though the evaporator is taking in latent and sensible, we're taking in just regular temperature and humidity heat. We're bringing that back to the chiller. What we've actually done in that process is we've converted that heat into just a sensible form, so that now we can flow that through our air-cooled condenser and we can reject it in a sensible form. So air-cooled systems are not affected directly in terms of heat transfer. Now, you get into corrosion and stuff, but they're not directly affected by humidity at the outdoor system where the coils are. So if you've got a very humid place or environment, that's not going to have an impact on you. So just in case that is not clear for anybody out there, just putting that clarification out. Hopefully that helped. I see from India, but you're working in Kuwait. Now, I don't know. I know that Kuwait is really close to the sea, so I'm very limited in my knowledge of this region. On some level, I actually know it's so. I would imagine you probably do have higher humidity problems because um, I've worked with some companies based out of the UAE, and they deal with a lot of humidity because they're right there off of the coast, and so or specifically like in the Dubai region. So I would imagine in Kuwait you've probably got a similar or a minimum closer to the coastline. You've probably got a similar issue though, where you've got a fairly humid area because of your proximity to the coast there. So I don't. I'm just making assumptions based off of where you're saying you're operating out of. Um, anyway, if you'd like to connect, if anybody would like to connect or work together, anything of that nature, you can always send me an email at hvactime at hvactimetx.com. Or the better place to do that is once you get into Chiller Academy, you see the logo here. Once you get into Chiller Academy, I've got a community page. I've got a whole system built out over there where we can connect, communicate, and that is my priority with any form of communications. Whoever is in the academy, like I will take care of you first there, and then whatever extra time I have, I try to help the rest of the community as much as I can. But my first dedication is to the students and the technicians in Chiller Academy. So just putting that out there, because sometimes if it can take me a while to get to non-academy requests. So what is delta P in York centrifugal water cooled chiller? Yep, good question. And I can actually pull this up. So let me get my setup going here. That. Make sure everybody can see it. Okay, and then I do have some pictures. Let me pull a picture. We can actually look at a control panel. This one should have it. It's thinking. Come on. Can you still hear me? There we go. Oh, yeah, the compressor. And we got delta P on here. Oh, no, we don't. Wrong one. 1 second. I'd like to actually show it to you so we can discuss it from there. I don't think I have a... Do I have a surge map? That'd be even better. Do I have a surge map? Maybe this. Man, that one still doesn't have it. If I can't find it here quickly, I'll just give up on the picture. And I'll just explain it. Here we go. Bam, surge map. Okay. Perfect. All right. So let's discuss this. We'll come back to this in a second. What is delta P over P in York centrifugal chiller, water cooled chiller? So delta P over P is basically compression ratio. It's taking your condenser pressure and your evaporator pressure, dividing those into one another, and giving you a ratio. Okay, so that is what compression ratio is. Now, I'd have to verify. I don't remember if York is actually taking proper compression ratio or just a kind of a raw literal delta P over P, because proper compression ratio is taking your absolute pressures. So you're taking your pressure reading inside the chiller, and then you're converting that via your atmospheric pressure wherever you're at. So for me, I'm fairly close to sea level. I'm not that far off, so I use 14.7. So you add that to your gauge pressures that your transducers are reading, and then you divide those into one another. That gives you compression ratio. I don't remember if York is actually doing that, or if they're just taking the raw actual gauge condenser pressure and gauge evaporator pressure and dividing them into one another. So either way, that is what it is explaining to you. And what is using this for is to control the surge condition. So we have our delta P over P down here. So this is the surge map inside of the compressor screen. You do need to be in a service mode, and then you have to input a special password to get into the surge map. It's a whole process to get into here, but there'll be a little O that floats around. So this green box is your indicator. There's an O. Let's see if we can find the O on here. This example may not. Is this machine? No, it's leaving water control. It should be on, but we don't see it. Huh. Either way, oh, there it is, right there. That little asterisk, that is indicating that this is where we're at currently on the map. So, well, this says output frequency. Yeah, so the system is trying to add, anyway, ignore this map. So you can see down here, this is where you're actually at, present condition. So it'll float around on this to show you where you are. And you can manually add these points. So basically what happens is every time a surge happens, it's comparing the delta P compared to the PRV, the pre-rotation vane, the guide vanes, where that is on this graph in correlation, and then it will map that point. And basically it wants to know that, okay, if I have this PRV position with this ratio, then I don't want to operate at that point any longer than I have to. And so it will do its best to intentionally skip that area of where the PRV and delta P correlate, so that you can prevent a surge. And that's the whole purpose of this, is to prevent a surge. So that is your delta P over P with a York YK centrifugal. It's just a form of compression ratio, and this is one of the ways that York uses it in mapping the surge map. Now, I'll get a little deeper into this while we're here. One of the things you have to be careful with is this map will clutter up. Now, York does not recommend clearing this map, and they have gone out of their way to make this to where unless you're already trained and know how to do this, getting to this point is quite difficult. So either way, I'll give a prime example. If the condenser water pump had an issue, you had a strainer issue, you needed a PM, and that's going to start causing major head pressure increases because of whatever happened on the condenser water side. Pick a symptom or a problem. One of the symptoms of that problem is you're going to increase head pressure, you're going to increase lift, and you're going to deal with a lot more surging at that point. That increased surging is going to start creating a lot of mapped points here. So those extra points on the map now become points that you're trying to avoid, so that the machine is intentionally trying not to continue surging, so that it protects itself, protects the bearings as much as possible. It's got its whole thing is trying to accomplish. And this is something that a lot of other chillers don't have. Either way, in that case, as soon as you've got that condenser water problem resolved, then if it took a minute to get it resolved and the chiller still had to run during the meantime, which, I mean, while it's not ideal, these things happen. We can't control all the conditions at our plant. Sometimes we just got to get the chiller to grunt through it. It's unfortunate, but true. So in that case, all those points now become a roadblock that isn't actually supposed to be there. Under normal conditions, some of these may not be points that would actually surge. Like this here may not be a actual surging point. This point may have graphed strictly because we had a condenser water problem. And if this whole, and I'd have to find the pictures of it, but I've had these where literally this whole left side of the map, which is where most of the points are going to graph, is nothing but a big just white X. Okay, that's not okay. That's not normal. And what that will cause is it's going to cause your especially with a variable speed, we have output frequency, right? So this is a variable speed system. It's going to cause this to max out at 100 at full 60 hertz all the time, or 50 hertz if you're overseas. So you're going to be sitting up here in the maximum speed all the time. And that is because we're trying to not go into a surge condition, which means we have to maintain a minimum speed. Because if the compressor was allowed to slow down, then the surge map is telling the machine that, well, if you slow down at all, I'm going to go straight into a surge, even though the problem that was causing the surging has already been resolved. So just something to be mindful of. That is a condition where you really do just have to clear the map and allow it to remap itself. That means that the chiller is going to push itself into some surging for a couple of days or so, off and on, until it remaps the actual points that should be there. And then it can avoid those, and it will allow it to go back into its normal, because part of what happens with that case is the machine can't unload effectively and run as efficient as it needs to. So that compressor will stay ramped up at high speed even though you may have a lower load, and then you can start pushing into cycling shutdowns, which is not a good thing, right? We don't want the chiller to shut down any more than it absolutely has to. So if we're shutting down on leaving water temperature because we can't unload the compressor, that becomes a problem. So that is a symptom the surge map can create, where we're staying at a high speed that's keeping us partially loaded, whereas if we could slow the motor down with the drive, then we could unload it significantly and we could still maintain operation with that low load condition. So that's just, yeah, this is an example of how that surge map is working, what delta P is being used for inside of that YK panel. And yeah, it's a form of expressing compression ratio, which is just another way to say lift. Okay, so compression ratio and lift, like, these things are different forms of saying something similar, and we use them in different ways. So lift, in my opinion, lift is just a simplified version of saying compression ratio. Now, most of us field guys, we can't do that kind of mathification in our mind, especially when we need to make really fast determinations because the conditions may be swinging so quickly. And so we really need to be able to look at the data and make a pretty quick analysis of, this is what's happening, these are my symptoms. And I can't do that kind of math in my head. Even if it was just strictly gauge pressure over gauge pressure instead of absolute over absolute, right? Even if that was true, I can't. I'm just, that's not me. I do know people who are that way. One fella, his name is Kirk. Holy hell, is he a math whiz? And he could do that kind of stuff in his head on the spot. I'm just not that guy. Anyway, that's where I see as lift became really useful for us as chiller techs, because instead of trying to do math, we can, or instead of trying to do division, I should say, we can just do a simple subtraction, and it's just condenser minus evaporator pressure that gives us lift, or, and better yet, saturation. So condenser saturation minus evap saturation, that gives you your saturated lift temperature. And that can help guide you on whether or not you're running a high lift or low lift or whatever the condition is, so that you can troubleshoot that machine really, really quickly. All of these things are just different ways of expressing the same basic information in a slightly different form. And it depends on what you're trying to use it for, right? So it just strictly depends on what the purpose of that data is and how it can help. This is just what York has chosen to use to simplify their process. Good question. All right. Hope you're doing well, everybody. I hope you had a good weekend. Hope you're having a good Monday so far. If not, let me take the bad Monday for you. I do see some internet kind of dropping in and out here, so I do apologize for that. The recordings of all this will get posted later, so if you missed a key point, don't worry. I've got all this recorded on my side with a clean feed, and I will get those posted accordingly. And if you have any questions, it's open Q&A. Okay, so there's no theme, no topic, or anything like that. You got a chiller question, stick it in the chat. So far, I'm focusing on the chat questions at the moment, and we'll go from there. All right, centrifugal chiller gas remove recovery system explain. Okay, so you're asking about doing a recovery. Sure. Let's talk about it. And to talk about it, let me actually, let's get a example pulled up here. Ooh, no, not that one. Let me find one I want to use. Give me just a second. I'd like to find a simpler one. I've been using one of my ones I did where everything's in series recently, and it causes a lot of confusion for many, which I get it. I get why it's confusing. It's just not a normal setup when you run your tanks in series, so I can appreciate that. Let me see if I want to find one of mine that I didn't do that in. One second. If I can't, I'll just grab my normal go-to if I can't make it quick. I have one of these here. No. Let's take a look at this one. Yeah, that'll be our out. Yeah, okay. We can use this one. I will zoom this picture a little bit. Maybe we can see it a little bit better. Okay. Centrifugal chiller gas remove recovery system explain. So we're just talking about centrifugal chiller recovery process. Now, I do have a set of service procedures in my service training program at chilleracademy.com where I go over this. I cover low pressure, I cover high pressure. I discuss it from a push-pull perspective, which is my recommendation. I also discuss it from a direct recovery. If for some reason push-pull is not an option for you in any case, which there are some circumstances where it happens, then you can implement a alternative, direct recovery, standard recovery would be another way of expressing that, instead of trying to do the push-pull route. So all of that is in Chiller Academy under the service training program if you would like some step-by-step guides of this process. Now, we'll do a quick overview of it now. So this would be this is a Trane CVH. So we've got a 1,000-pound cylinder here, and doing a recovery. This would be a RefTech recovery unit. This up here is your suction elbow with vapor going back in, and then down here at the bottom there is a liquid charging port that we're pulling from. So this is an example of a push-pull recovery setup, and this is my recommended way of doing any of these. This is a low pressure chiller, but it would be a exact same setup with a high pressure in this particular case. Now, there are some minor variances when dealing with the pressures because of being low pressure versus high pressure and how we purge and clear the lines. There's some little details there, but on a high level, this is the basic setup. So what this machine is doing is the recovery machine is drawing a slight lower pressure, or I mean, it's all in a vacuum in the end, on this recovery cylinder. So this recovery cylinder should have already been pulled into a vacuum prior to starting this recovery. So once you open the valves, you should be at a evacuated state where it's going to start drawing liquid refrigerant in directly off the bottom of the evaporator. Now keep in mind, make sure you are flowing water through these through the tubes when you're doing this process. If the with using push-pull, freezing tubes is less of a concern. And I do say less, not no concern. It is less of a concern because technically we're not dropping the pressure on the chiller. So our liquid refrigerant should not get below a freezing temperature. Should is the key word I want you to hold on to here. So if you're not comfortable with doing this process or you haven't done it that much, always make sure you're flowing water as a safe precaution. Flowing water can also help make it a little easier by adding heat to the barrel. It can make it easier getting the refrigerant to want to move and boil off and do what it does appropriately. Either way, getting back to how this process is working. So we open this valve. We're going to have some form of refrigerant flow in on its own by opening the liquid valve. So we're coming in off of the bottom of the evaporator into the liquid valve of this tank. And then out of the vapor side of this tank, we're coming back into the inlet port of our recovery machine. So that's coming in here. We're going to flow through the recovery machine, back out of the outlet port, and push that vapor back into, in this particular case, the suction elbow of the chiller. So I said this is CVH. Actually, I think this is a CDH. So this should be a dual compressor. This would be compressor 1. This should be compressor 2. So I think this is a CDH. Either way, sorry. So we're pushing that vapor back into here. And then essentially what's happening is there is a lower pressure on this cylinder than the refrigerant pressure of the evaporator, which causes a draw into the cylinder. At the same time, we're maintaining a pressure on the evaporator by pushing that vapor back into the chiller, and it creates this self-looping process where as we're pulling here, we're pushing back here, and this liquid refrigerant charge is getting drawn out of the chiller and into the recovery cylinder. And this is happening, no liquid refrigerant is flowing through our recovery machine. We should be monitoring our weight, and having sight glasses is ideal here at the recovery cylinder itself, so that we can make sure that we're not accidentally having liquid come back. These particular styles of recovery machines are not made to process liquid refrigerant whatsoever, like we do with, say, like a G5 Twin or a Navic recovery. Those can actually process some level of liquid if you use them correctly. Okay, using them correctly is a big caveat there, but these are not. So you got to make sure we're being cautious of that. We're monitoring how much refrigerant's in this cylinder and where we're at. If we have to transport it, we have to make sure that we're not going over 80%. Good rule of thumb is just not exceeding 80% in general. But again, if you have some experience and you have some understanding, you'll know what I'm talking about with the 80% rule there. Okay, if you don't, then just don't worry about it. You don't need to risk anything. It's not worth it. Just stick to the 80%. So that is the basic process. We're going to use this, and we'll change out cylinders as we need to in order to get all the refrigerant out. But it'll we'll recover this down to the till all the liquid is gone. That is the ultimate goal. We want to get all the liquid out via this push-pull and in here, which there's two ways of determining that. Or I guess technically three. One, you could have a sight glass here on the liquid line coming into the tank. When that sight glass goes to, I guess just vapor, it's no longer liquid flowing through there, would be the simplest way to say that. Then you've got the liquid refrigerant out of the evaporator. That's where the refrigerant's going to stack on most of these chillers. It's going to all be in the evaporator side. Now, if you are another way to do it would be weight. So once we know that we're hitting our weight, we know that we're going to be finishing off the little bit of liquid refrigerant that is in there. And another way to do it is the hose itself. So when liquid is flowing through these hoses, it has this kind of jerkiness to it. So it'll kind of flutter around it, and you'll see the hose physically moving, and what you're seeing is the liquid refrigerant traveling through that loose hose, and it's heavy enough to cause the hose to have some movement to it. And you can actually hold your hand on it, and you can feel that liquid going through there once you understand what you're feeling for. So if that hose is still dancing around a little bit, and it's not always much, but then you know that liquid is still processing through there. This is my actual preferred method that I use myself all the time. Like, I'm actually watching my hose, and I can tell based off how the hose is acting. Now, once the hose goes still, and you don't see it kind of dancing around, and you don't feel it anymore, that is an indication that you now just have vapor refrigerant flowing through there. You no longer have a heavy liquid making the hose dance. It's just vapor. So that's another way of determining if you've gotten the liquid out and you're going to a vapor. Once you get all the liquid out of the circuit and into the recovery machine, or into the recovery cylinder, I mean, all you're doing at that point is you're just cycling vapor around in a circle. Okay, so the push-pull process only accomplishes getting the liquid out of the chiller. So the next stage of that process would be going into a direct recovery phase. So at that point, you'll reconfigure everything, and essentially you'll swap the hoses here. Okay, so you can close this liquid valve between the tank and the chiller. I would close it on both ends, and then close all your valves. Swap your hose connections to where the tank vapor is on the output and the chiller vapor up here comes into the input of the recovery machine. Once you swap those around, then you can start doing the vapor pull process to get the rest of the refrigerant out and into your cylinder from there. And most of the time, these machines will come with some form of built-in subcooler if you get the right models. Some of them can have air-cooled. I personally prefer the water-cooled version. Either way, you'll be able to process that vapor down and keep your tank pressure down as well, if you even need it. In some cases, it's just not even necessary with the amount of vapor we've got left in there, or given our plant conditions, whatever the case may be. But yeah, so the first phase of the push-pull process gets your liquid out. Second phase is getting your vapor out, and then you're done. That is the basic recovery process of a centrifugal chiller, water-cooled. Yeah, that's how we get everything out and process it through there. Again, if you'd like an actual step-by-step guide and all my little notes and details on how I would specifically recommend applying this to chillers in general, the processes are all still roughly the same, then go check out my service training program over at chilleracademy.com. Really good question. Yeah, I appreciate the support, guys. I don't have a WhatsApp number or anything that I give out currently. These are things I've considered over time, but it's not something I currently have or am able to offer. Right now, it's everything I can do just to keep up with the current needs of students in the academy and stuff, and that is my primary focus. And so trying to expand that outside of that right now is just not currently possible. As things continue to develop, I do have ideas of bringing on more senior people. I even have the idea, like, none of us enjoy retirement. We're just not the kind of people to sit around in retirement in general. So it's like, okay, well, there's actually probably some really good retired chiller techs out there who would just like something to do and have fun part-time. So having a support line, support service, something like that is one of the ideas I've had of something to develop and build a really good team that can help with that. That's just not something I can currently do, and other people not suffer for it. So anyway, have you ever seen a McQuay centrifugal compressor? We use this compressor. Yes. So is it Tejas? If I'm saying that right. If not, I'm sorry. Um, yes, I am familiar with McQuay's. I don't have. I mean, I've worked on them less than I have York and Trane as an example. So I don't have them quite as hardcore memory as I do some others, but I've definitely done plenty of hands on with them. So feel free to hit your question in there if you have it. Um, yeah, if somebody has a question, let's see. Yeah, go ahead and get it in. Otherwise, I can jump over to the um, uh, I can jump over to the reserve questions and pull from one of those. So just giving everybody a moment to um, jump in there with that if you'd need it. Silence this. Hope you're having a great day. Hope you're having a great week. It's been pretty good so far on this side. Had the fire department fundraiser over the weekend, so that was fun. It's a lot of work putting all that together and whatnot, but it's fun to get to have the community come together and um, meet new people, see who all's around, connect with people you've known for a long time, right? So it's a really fun community event to come together and us with the so I'm with the volunteer fire department, us to be able to um, connect with the community that we're serving, right? That's a pretty cool thing. So it made it for a busy weekend though. I'm still pretty tired from it myself. It's a lot. It's a long day, late nights. We got to the firehouse. We'd already spent most of the week kind of working on it. We got to the firehouse at 8 o'clock that morning and didn't leave until 11 that night. So it's a good weekend overall though. Everybody enjoyed it. It's fun to see the kids come up there and get involved with the fire trucks and stuff. Okay. Let's do this. Get the next question loaded up. This one's a little bit of a longer one. Just bear with me. Okay. Many designs I see in buildings spec their machines to run at certain condensing temps, artificially high, like 95. Goodness, 95 degrees. Why not aim for lower temp you can manage or even get your condenser water down to true ambient, like 70? And this is a very good conversation that I don't know, there's the opinions around it could go a few ways. Um, on one hand, I found that some sector of building um, energy optimization. So there are people out there that specialize in optimizing a building and their energy profile, which includes very heavily the HVAC system. But what I find is many of these people are looking far beyond just the HVAC. Their specialty includes a whole gamut of um, energy usage. So how you control your lights and the staging sequences of the lights themselves, and how everything turns on, what humidity levels, which I guess is us, but like there's a lot that goes into what they're gauging to control or help optimize the efficiency of the building. And what I have personally experienced with some of these is they do believe in either raising condenser water temps, it would be one, so that their idea is they're trying to draw load off of the cooling tower and make the fans run slower. or well, I guess yeah, that is the main concept that they've always given me, is they want the fans to run slower on the cooling tower, and so less amperage, less energy, right? If as if it was that simple. I'll get to that in a moment. So there is one sector of people that, yeah, as part of the optimization piece of things. Now there's another side of this where we're at the tail end of the generation that did not have advanced automation controls, but there's still plenty of people out there. So, um, and sadly, I would go as further to say that we still have those guys apprentices who are now, the journeymans, if you will, who never kind of move past some of those same mentalities. And the reason I mention that is the original and early control systems were not easy nor that effective to set up for variable condenser water control, or for set point control, where the system could auto tune its condenser water set point. Those systems were not developed far enough to be useful, which is not true in today's environment. We actually have control systems that it's very easy to set something like that up. So those are the two camps that I see people come from, where either they're just not up to speed enough, which is just basic training and just evolution of things. They're just not up to speed enough to understand using the control system at a higher level, or they've been taught through optimization that they need to get all motors to run as slow as possible, right? So, I mean, part of what they do is they'll lower the static set points on these buildings. That's something they'll do at the air handler levels, right? More than just try to get the condenser fan or the cooling tower fans to stage down. They'll also go as far as they'll start running super low statics on all of the air handlers, so that they can you slow down the air handler motors and again achieve Energy Star ratings and all the other jazz that they go for. And so a building that needs to run 1.2 inches of static for smooth operation, they'll turn around and drop it to 0.8 and be like, oh, it'll be good enough. Industry standard is 1 inch. Da, 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 da. It doesn't need to be 1.2 is too much, even though. Anyway, I'm get off on a tangent with that. I've had lots of dealings with energy management optimizers, if you haven't, and I've just anyway. So, here's my approach to this and pitch that I would give. Now, our ultimate goal for condenser water, so being the fact that we have condenser water temperatures, means that we've got a water cooled system, period. Our goal, in my opinion, should be to try to maintain as low of a condenser water as that chiller is allowed to handle, and do that as effectively as we can so that we can lower the amps. Because in most cases, unless we're dealing with just really small equipment, in most cases, by a couple of degrees or several degrees of temperature change on the condenser water can mean significant load reduction on the compressor, because its amount of energy is directly correlated to how hard it's having to compress. So the higher we force our condenser pressure, the harder the compressor has to work in order to achieve the condenser saturation that we need in order to allow for the proper heat transfer process. And so if we are trying to save energy by slowing down a 50 horse motor in a cooling tower and dropping it by 10 amps, but that means that we're, instead of being able to run a 75 degree condenser water, now we're trying to run an 85 degree and just run that fan a bit slower, those 10 amps are substantially multiplied by a huge factor in the compressor, because now instead of trying to get that low pressure refrigerant to 75 degrees of saturation, or I guess let's go to 3-degree approach here. Okay, so instead of trying to get it to 78 degrees of saturation on the condenser, now we've got to get it to 88 degrees of saturation. That's a pretty big difference. And that requires, 10 amps at the tower fan turns into 50, 60 amps at the compressor. Now, these aren't hard numbers. These are just examples, but this is realistic to what I personally have dealt with in these cases. And so it is way more efficient to put the extra load on the tower fan, and it's a hell of a lot easier to fix a tower fan motor than to try to service a chiller that's been beat to hell because we're trying to run high condenser waters. Whether it be a surging issue, that would be the worst case scenario, right? You artificially trying to use less energy in your cooling towers by raising the condenser water set points, but now you've pushed your chiller to a point where it's more frequently surging. Well, now you've substantially increased the likelihood that you're going to end up having a catastrophic failure due to the surging conditions, which is then going to turn into $100,000+ overhaul, just depending on circumstances, just to get the chiller back online, not to mention the downtime and everything else involved. That's what we're discussing here. That's the difference. So to me, it makes absolutely no sense to artificially run really high condenser water temperatures just to save on the tower fan, which, worst case scenario, the worst case scenario I've seen, you got to use a helicopter or a big crane to pluck the tower fan motor because of its size and location, right? That still end up being a lot cheaper than trying to overhaul the compressor. Not to mention all the extra energy you end up using. And what I've seen is these people are good at their job most of the time, these optimizers, okay? So I'm not taking that credit away from them. And what ends up happening that I have seen is they'll do these things and they will end up showing where they've reduced the total energy usage of the building. And so they have this positive feedback loop to think that, okay, well, by setting that high condenser water set point, that ended up, taking a lot of load off of that was part of the bigger picture to take the load off. And we're now more efficient because of that. When in reality it's all the other things that they changed to help that building operate better that did lower the energy profile, but they did end up increasing the chiller's energy profile because of that condenser water set point. And if they would have done a better job on the condenser water set point, they could have reduced that energy profile even further. But they don't see it that way because they just don't, they're not chiller technicians. They don't see it from our perspective, and that's okay. That's their job, and this is ours. And this is why we have to work alongside people like this to help mitigate these little things. So, okay, so I've gone on this whole spiel about set points and not artificially raising them. It's better to put load on the tower, not the chiller. What actual solution do I recommend? What is my go-to with that? Well, it is having a variable condenser water set point. To me, this is the perfect middle ground. And all it takes is a temperature sensor and a relative humidity sensor on the outdoors tied into the control systems. And most control systems nowadays, especially your regular PLCs, programmable logic controllers, so you're talking your Honeywells, your Distechs, your Johnson Controls, your Trane, all of these have basic control algorithms already built out for variable condenser water control. So once you have just the temperature sensors, it's not that hard to integrate the PID required to control this, the algorithm that we need. So you need to know your tower's approach. Okay, so tower approach is the difference between the leaving water temperature and the wet bulb temperature. That is your cooling tower approach. Most generic cooling towers are about 5 degrees of approach. Some really high efficiency ones I've seen get as low as 3 degrees. Some really beat up or older towers, or if they're not very well maintained, may run more like 7 degrees. So you do need to kind of figure out what is your tower approach that your tower is able to do. 5 degrees tends to be a pretty even baseline for most towers. So what you'll end up having is your control system can calculate wet bulb by taking the ambient outdoor temperature and the humidity, plotting that on or converting that into a wet bulb temperature via psychrometrics. Okay, very basic stuff. And then we can plug the output of that calculation into the control circuit, or the algorithm to control leaving water set point, or the condenser water set point, damn it, to control the condenser water set point. So essentially it is wet bulb temperature plus 5 degrees, with a 5 degree approach, let's say, equals your condenser water set point. And let that be a variable set point. Okay, now I take that a step further to where we need to set some minimum and maximums based off of our chiller. So with a lot of chillers like your RTHD or a CVH, CDH, those cannot operate with cold condenser waters. They need that warmer water to maintain proper oil return, because part of what happens is if we drop that condenser water too low, the adductor system can't recover the oil back properly because we're using hot gas off the condenser to feed the adductor circuit. So if we do not have enough velocity on that hot gas, then we cannot properly create the Venturi effect, the siphoning effect, to draw that oil latent refrigerant back off of our evaporators, which then allows it to stack up. Or if we have a gas pump, being able to properly push that that oil latent refrigerant back up into the compressor, an RTHD example. So that's the consequence of getting too low. So usually with those, 70 degrees is about as low as you can safely operate. And I personally may set a minimum, or the lowest it can go to about 75 on a machine like that. I personally like to play it a little safe, but I'll set the maximum that one can go to like 85, maybe even 90, depending on the circumstances. Okay, depending on the plant. I've even gone as high as the maximum that temperature can go is 90. And so then at that point, it'll control that algorithm, wet bulb plus 5 equals your output within this window. And then the control system can vary the fan accordingly. And then we're not actually putting any more load on the fan than we absolutely have to make leaving water set point, which allows us to not have to run the fan at 100% all the time and still get the maximum amount of leaving water temperature, the lowest value we can get for that chiller. Now, if I was dealing with like a YK, those can operate at a much lower temperature, but they don't do quite as well at the higher temperatures most of the time, especially if I've got a site that doesn't typically load that chiller up all the way. So with a YK, I would set the same formula as to how we're calculating it, but I would set that lowest set point minimum to about 65. Now, York says you can go as low as 60, but I prefer about 65, but I'll cap out at 80. So I'll let that one swing between 65 and 80 instead of the 75 and 85 to 90 with a Trane, as are just two baseline examples here. So that is my approach to this, and it's, once you get everybody bought, like the hardest part I've found is just getting everybody bought in on the whole concept. Not only from the facilities team, but even your automation team. Sometimes, like, everybody else has to buy in that this is worth the time. At that point, it's not that expensive, and it's actually pretty easy to just roll that out and implement it most of the time. It's just, yeah, I've had a harder time getting people to understand this well enough to agree that this is the best direction forward. Like, that's been my biggest issue I've had.
either way, what that does is it allows us to keep the compressor load as minimized as much as possible without overtaxing our cooling tower, because you will not, that tower cannot overcome that wet bulb temperature, because the whole operation is based off of evaporation. And so when we start getting up on top of that wet bulb temperature, we start to get past a point where we can now evaporate. So if we've got a wet bulb of 80 degrees and we want to maintain 80 degrees of condenser water, the tower's just never going to get there, because it has an approach value of some kind, but we're just, evaporation isn't going to continue past that wet bulb temperature. That is as far as evaporation is going to allow that temperature to lower, which is what our wet bulb is. So, yeah, we can optimize how much load is on the tower to minimize the stress on it, while also helping minimize what our compressor load is at that time. That is my rant on condenser water set points and how people have managed that over time. I've had this conversation so many times, so it's shocking how much it comes up, but I get it. Like, it is, call it a hot topic. I don't know. Anyway, questions? All right. How to connect? Yeah. So on Chiller Academy, like even on the free service course, you can go into the comments and like say whatever you're trying to do. If you've got further questions, you feel free to use the comment section inside of there. I do keep up with that. Now, once you're enrolled in one of the paid trainings, especially like the certification course or the service training program, one of those, you do get access to the internal community. And that internal community is where we can go a lot deeper and, post videos, post pictures, share information on a much deeper scale inside of that community. So, in terms of, connecting there, that is the best method inside of the academy. Now, I also try my best to keep up with which students that email me are academy members. That is a little bit harder to do, but I try to prioritize who I know is enrolled in the academy when I do have emails come through. Why York display hanging? Mudasar? I'm sorry, I don't know how to correctly say that. I don't know what you mean by York display hanging. I will need some better context around that. So I'm not sure how to answer that. So if we do have another question, now's a good time to get it in. I do have some other questions in the log I can jump to. So if you do have one, get it in the chat, and I will be able to get right to it if you'd like to get that in. Yeah, so our goal here is to just answer the questions in a chiller tech context. That's one of the struggles you'll have as you try to do online research and look into things, is getting answers in the correct context. Is difficult and is misleading at times. Sometimes the answers you get back are for very different context other than like how we would use them as a technician. So one thing I want to really accomplish here is that you're actually getting responses in the correct context here. And then we've got the pregnant lioness herself in the chat here today. asking about her back rub that she was promised later today. Don't worry, honey. I will get to it. And as you have learned via 4 kids later, pretty good at the back rubs by now. Just saying. All right. So let's dive into the next one here. Oh, wait. Will it make a difference if we place ice on the cooling tower basin? Can it help the chiller in the long run? If we place ice, that's an interesting thought. Okay, so let's discuss that. I haven't been presented with that idea before. So let's... Come on. Let's talk that out. Will it make a difference if we place ice on the cooling tower basin? Can it help with chiller in the long run? Well, so one of the things ice is doing is ice would be able to lower our temperature beyond wet bulb. So if we had a situation where we had an extremely high wet bulb and we weren't able to get the tower, the condenser water temperature down, then what ice is doing is ice would be adding another cooling source, if you will. Right? So could we cool beyond wet bulb at that point, having ice in the basin? Yeah, because we have an external source of cooling that's not based off of evaporation, right? So now we're no longer trying to cool via evaporation. We're instead just using a sensible conductive transfer where we've taken water that's been pre-chilled somewhere else to the point of being ice, and then now we're adding that frozen water into the basin, which is then going to allow us to further cool that basin temperature. And if we add enough ice and it doesn't get sucked into the pumps or anything, because you don't want that, but if we add enough ice and we can run the system safely, then yeah, we could get that tower water theoretically down as far as we wanted to go. But at that point, you're adding another form of refrigeration to the cooling tower process. And we're no longer basing our ability to make set point off of what the ambient conditions are anymore and our ability to evaporate within inside of those parameters. Does that make sense? So can it help the chiller in the long run? I mean, again, this does come back to we can only go so cold at the same time. So if doing this method and adding ice also means that we start pushing the lower boundaries of how cold of condenser water we're feeding to the chiller, well, then we get back into oil migration territory where we're not properly pulling the oil back into the sump, and the oil recovery system in the chiller, the adductors, aren't able to function correctly, right? So at the same time, in all fairness, as long as we're within those parameters, the lower we can maintain that condenser water within the safety limits of that particular chiller, yeah, the better it is for the chiller in the long run. Because, again, as long as we're inside of parameters, the lower that temperature, the less our head pressure, the less work being put on the motor and all the other electronics and the mechanical components. You know, our bearings are a part of that. When we've got really high lift conditions, and then we are putting a lot more stress on our bearings to support the forces being applied on our shaft and our impeller. So that does have an impact on everything's longevity. So if we can reduce that stress and that amount of work it's having to apply, then um, we will end up better in the long run. Yeah. So in all fairness, absolutely. Would it be better if that's what it achieves? Then yes. Yes, it would be better. It can help. Uh, yeah, but then we get into the rest of the context. Okay. That is an interesting thought, though, because you could take that into a number of directions, right? In the same way, again, engineers somebody able to do math better than me would have to sit down and run the calculations and how much energy it took to chill the thermal bank, and then how much energy or how long that thermal bank would last in conjunction with the condenser water loop, and then you factor the cost of creating that versus the cost of just allowing that wear and tear to happen on the chiller, right? And so then is reducing or increasing the life expectancy and reducing the stress on the chiller, does that cost make up for the cost to do the thermal bank and having that much ice added to the tower? Like, there's this whole give and take cycle we fall into on what makes the most sense financially. Because even if it helps our chiller run longer with less stress, it it doesn't mean that it saves us money in the end, because it may cost us more money to achieve that efficiency and that lifespan than it would have if we just let the freaking thing destroy itself, in under a normal life cycle. And we would be cheaper and better off just allowing that normal cycle to play itself out, right? That's kind of that's the whole dynamic of, that's probably why thermal banks on condenser water systems under normal circumstances, at least that I'm aware of, they're just not really a thing. It does make sense on the chill water side. And that's a whole nother rabbit trail to dive off into, is thermal storage systems. And anyway, yeah, so that's part of that. What's the trade-off? Because there's trade-offs somewhere along the way. Yeah, you'll increase life expectancy and efficiency, but it's going to cost you out the ass. you know Let's see, Amelia, I am 20. I have 1 year of experience in residential. How can I start learning about chillers? Looking to move up as fast as possible. I've heard you say that residential experience does not translate to chillers. Where did I say that? I'm trying to think of the context there. This is worth talking about. Let's have this chat. Absolutely. I am trying to think of the context of which I would have made those comments, because there is some truth to it, but it's not the whole picture. So I do think it is possible that I have made a comment like that. Yeah. Just give me 1 second. Let me get all this loaded up here. Okay. Bam. By the way, Emilio, welcome to the channel. Welcome to the chat. Welcome to the chiller community. Guess what, Bubba? The fact that you're here, you're already on your way to becoming a part of it, if this is what you want to do with your career. I'll say this up front. This is part of becoming one of us. One of the chiller guys is getting involved with chiller guys and asking these questions, having these conversations, and beginning to this learning process. So, you want to become a chiller technician, then get involved with chiller technicians. That's one of the fastest ways, and this is one of the simplest answers I can give. So welcome. Is my overall point. Welcome, welcome. All right, I am 20. I have 1 year of experience in residential HVAC. How can I start learning about chillers? I am looking to move up as fast as possible. I've heard you say that residential experience does not translate to chillers. Residential is a very different animal compared to what we do on the chiller side. And by chiller side, an even broader way of saying that is heavy commercial industrial side. Who we're working for, what we're working on, a lot of things are very different. So residential is operating at the, and this is not to put anybody down, okay, but it is operating at the most basic foundations of what our industry has to offer. Now, there are some residential systems today that have started to use some of our, say, more advanced technologies, such as variable speed, whether it be via drives, whether it be via ECM, or communicating systems and using a 2-wire or 4-wire data communication. These are things that, from, let's just say, to the chiller side, we have used for decades. And residential is within their first decade, I would say, of this really becoming any form of normal. And even then, it's really not that broadly used, unless you're dealing with a mini split or something. So I'll give you that. But in terms of regular split systems, not unless, again, unless they're paying for a really high-end residential split, most of your residential splits are still not using a communicating data bus. But these are things that we have used for a very long time in the chiller side. So part of what I want to express with pointing that out is, in residential, you are learning the core fundamentals and you're building a basic tool and knowledge base on how to operate as a technician in this industry. And like the fundamentals of refrigeration are all still there. And one of the things that I'll bridge a gap for is, with chillers, what makes a chiller a chiller? The simple answer, it has a hydronic evaporator. Hydronic, it has water, or you'll hear the term brine. Brine being a glycol solution. Why do we have that? So that we can run colder leaving water temperatures out of our machines without freezing the water, because water freezes at 32. Sometimes we need to run at 30 or upper 20s in terms of temperature to achieve whatever process is happening, right? Those systems exist. So we have a brine solution, or maybe we just don't want it to freeze due to ambient conditions too. That also is true. Either way, so that's what a chiller is. But we use water and water through a chill water coil the same way that we would use DX coils, right? Which is just a refrigerant-based coil. Refrigerant flowing through the coil instead of water. I will point out, real technicality here, water is a refrigerant. Was it 718, I think is the R number? Pretty sure that's right. 718 or 713, something like that. It has a refrigeration R number. So just that doesn't really matter here in this context. Point is, we use it the same way. So the standard machine uses a 45-degree leaving water temperature, but most of your coils in a split system are going to be about 42, 45 degrees of refrigerant saturation. Those correlate for the same reasons. Dehumidification, right? Those are areas where these things overlap. These are the same basic fundamentals. We have less heat exchange through our air handler. We run lower saturations. If for example, our CFM, you get a dirty filter on your air handler unit, you run less CFM through your air handler, you're going to see saturation drop. You're going to see superheat drop, depending on your metering device, most of the time, right? Those things are going to correlate. instead of air for CFM, replace that with water and GPM on our chiller's evaporator. So now if we run less water through our evaporator in the form of gallons per minute, let's say a strainer began to plug up. Okay, so instead of a air filter, we now have a water filter, a strainer, that begins to plug up and lowers our GPM. Well, we're going to see the exact same conditions. We're going to see saturation begin to drop. We're going to see the superheat also be affected. These are fundamental operations that happen in residential and in chillers, but we're using slightly different mediums. Mediums are call it fluid, okay, that is processing through our heat exchanger. The fluid in a split system is air, ambient air that we breathe. The fluid through a chiller's evaporator is liquid water. Okay, so we're changing what is flowing through our evaporator, but the core fundamentals of what's happening on a refrigeration level aren't changing. Those things are staying the same. So there are plenty of things from a basics level that correlate. There's also lots of tools that correlate. We use the same service wrenches. Now, albeit there are larger ones, right? So you've got the 3/8, 5/16, quarter, standard service wrench, and we get into 1/2 inch and 3/4 service valves. Okay, so those would be some things that we just scale bigger because we have our machines are running at larger tonnages. We're trying to maintain an entire facility where you may be just trying to maintain a single house. And it's just a scale aspect at that point. So the tools scale up larger, but a lot of the same basic tools. We use the same Phillips screwdriver. We use the same 5/16 nut driver. These are things that overlap and correlate. Okay, so, but a lot of other stuff changes. Okay, getting back to the scale of things, on the chiller side, we don't operate with flat rate pricing. If you're in residential, you're probably familiar with having your price books that you drive around with and a vehicle fully stocked with all your different components. You've got your standard condenser fan, your standard blower motor, your standard capacitors that you would need. You've got all this stock on your vehicle. And you're probably carrying more stock than you're carrying tools. Well, this is a difference when you get into the chiller side. For us, we typically carry more tools than we do stock. Why? Because not only the scale and how big things are, but also the variety is just far too broad. We're not dealing with single phase where we can take a standard, we can have just a handful of basic contactors on hand at all times. That's not true for us. We have starters the size of my head, which means aka large, and we may have 3 of those for one motor. You can't carry that in a truck stock. So yeah, like these are things where we become different. We don't work off of flat rate pricing. It's just not possible. You can't create a flat rate book, in my opinion, doing chiller side work. That book would be so big, it just wouldn't be reasonable. There's just too many variables. That's just not how this side of the industry operates. We don't work off of commission, most of us. I have seen exceptions to this particular one, but most of us don't operate off of commissions the same way that you would in residential, where you get a commission, or a PIP would be another way of saying that, off of how much you can sell a particular customer. These are things that are different and they don't translate. Now, getting into learning chillers, one of the best ways, in my opinion, is exactly what I'm trying to do here. You're exactly who I'm trying to speak to right now. You're exactly why this live stream is happening. We need more people like yourself to get involved and try to grow into this side of the industry. We need people like yourself, and we need you to take this Have fun in the process, genuinely, but we also need you to take this seriously because there's not enough of us doing this, and we're struggling, and we're overwhelmed, and we can't get enough people to help us. And this is a major problem. Many of us, we're working too many hours, recession or not, down economy or not. There's not enough of us to support this industry. And that means that there'll be minor fluctuations with economy, but it's not a whole lot in the end. Not for those of us who are fully established with established companies, because there's just too much work. That down economy means just less backlog. That's what it has meant for 10 years. For 10 years of all these economic cycles, when the economy slows down, even during COVID, most of the time it just meant on the chiller side, we've got less backlog than we did a month ago. We're still not caught up. And I don't want to, I want to be, I'm not trying to be insensitive to some people who probably were affected by that negatively. I do, there are cases, but for the most part, like that is just kind of how it has gone. So, getting involved here on the channel and getting involved over at chilleracademy.com. I have an entire free course if you're interested in learning this. I have an entire free course for you to be able to go through and see what chiller life is like, and if that's something you would be interested in doing, and if that's a career path you really want to take. It worked out perfect for me. This is my dream career. I love chillers and everything about them. They're just so freaking awesome. So, in terms of getting on with a company, there's a couple of paths to go with that. Being you're this early and you're this young, yeah, there's lots of companies who are looking for good apprentices, because that's not always the easiest thing to come across, who they can bring in and train. And if you can come in, see, as a previous operations manager myself, when I have an apprentice who can come in and just completely lay out so much already work they've put in, they fully understand a refrigeration cycle, they fully understand superheats, not only just suction, but discharge superheat. They can express some form of understanding of hydronics and the basics there. You don't have to be an expert, and don't try to pretend that you are in any of this stuff. Be upfront with the fact that you're learning, but here's what you've learned, right? And just walk in with, I've learned this. I can't tell you how much that would go a long way with the right company to recognize that you're willing to put the work in, that they're willing to invest in you. And that's a big problem that a lot of us have. That's a conversation I have with a lot of owners all the time. How do we get our apprentices to put the amount of work in that we're willing to invest in them? Why? Because we have to. If there's nobody else to hire, they're not there. They don't exist. So we've got to do something, and that means being far more intentional with bringing up younger technicians. But that also means that you've got to be willing to show that you are willing to put that work in. So if you can find a company that works on chillers and has a chiller team, make sure you verify that piece of it. Then do what you can to get on board with them. Even if that means take a pay cut, I promise you it's temporary. Take the pay cut. If you want to do this, get involved. Let them guide you and teach you. It won't take that long before whatever you thought you could make in residential would be a laughing joke to what you can do if you can put the time in to be successful on this side of the industry. So if you can't, if there's not a company who's willing to do that, a next step would be finding a company that at minimum does heavy commercial. And get involved in the commercial side. Get out of residential and into commercial in general. Start developing your commercial understanding. Because the customers we deal with, the norms that we go through, There's just so many little things that you need to get up to speed on and learn in the process, to interact with customers successfully at a minimum. It's not the same thing as dealing with a homeowner whatsoever. So, yes, get involved with a heavy commercial company, not even light commercial, even though that is a step I took. I went residential, light commercial, heavy commercial, chillers. Okay, so I did go that path. But I would suggest to you skip the light commercial part. Don't get caught up in the low temp refrigeration side of things. That it's a tough industry. If that's your thing, go for it. Okay, but if you want chillers, if that is your goal, skip that. Find a company that's doing heavy commercial work, even if they don't have chillers, and begin to learn. You're in that environment. You're going to see all the control systems that we work on. You're going to see large circuit recoveries, charging. You're going to start working with cranes and a whole, like, there's so many little things that you will need when it comes time to trying to apply for that chiller role. And in the meantime, while you're working with that company that's doing the heavy commercial, learn chillers. Get involved at Chiller Academy. Get on these streams, ask your questions, get clarification, and learn this stuff in the process. So that once you get your feet under you, you can then approach a company that is working on chillers full time. And you can show them, hey, I've done this study. I've learned this. I've worked in heavy side on doing this. I need an opportunity. This is what I have done. This is what I know. Quiz me. Ask me questions. I don't have all the answers, but I think I have enough to be worth your time. Don't be arrogant, but stand on what you do understand. And if they correct you, so be it. Let them correct you. That is a conversation that can help guide you into a company to do what you want to do and to scale your career further into this industry. Yeah, that would be my high level direction I would suggest in what I see in today's market. So, yeah, just start learning and get into commercial, period. Just find somebody who's willing to give you an opportunity. Get into commercial. Show that you have the chops for commercial, that you can do this side of work. And then learn what you need to learn about chillers. I'm doing my best to build a resource for you so you can learn. That is my ultimate goal. We need you to help us. Anyway. I go live every Monday at 11 o'clock Central Time, my time, so I'm in Texas. So, yeah, I go live every Monday. So, yeah, you're welcome to join in anytime. And if you go to Chiller Academy, I have a portal for these lives. And if you have questions, I do prioritize those questions in the portal first when I open the stream. So you can go join that for free. It doesn't cost anything. You can only see all the previous lives and their breakdowns, but you can also get your questions in prematurely, so that I can go into the stream knowing that I'm going to knock out these questions first, and then we'll move on with the rest of it. So yeah, if you want to get into that portal for the live chiller training series, or no, I'm sorry, the chiller questions answered series. That's what everybody wanted to call this. That's the one you're looking for. Okay. We have just a few minutes. I may have enough time for another question. Let's see what we got. Last resort. Managing our chiller system in a tropical country. Oh, okay. Yeah, so I mean that makes sense, Dan, in terms of your condenser water issues. Now, The thing is, though, we can. I don't know what all you've done up to this point, but there are lots of things that can be done to help your chiller if you're dealing with condenser water issues. So, yeah, I see your point though in adding ice, and I don't know, it might be worth it. Having something like that might be worth it given your circumstances and what you've got going on. It there's extreme case exceptions to almost everything. I'd be willing to say that you're probably on one of those extreme case scenarios. Okay, so you may fit outside of the normal. All right, so if I apply good foundation for yes, Froggy, it is amazing how many people come in with years of experience. I've interviewed many residential people who are trying to get into the commercial side and could not properly explain the refrigeration cycle or even draw one. But they've been doing this. Well, oh no, no. So yeah, understand the refrigeration cycle and being able to very well articulate that cycle confidently. That's a big first step. I have 11 years of experience working for my father. I have lots of knowledge from residential, commercial, and refrigeration. I'm going to apply for my TA. Yeah, awesome. Do you think it's possible to jump in? I think it's possible to jump into chiller side, Stefan. Yeah, absolutely. So, if you want to get into, chillers, so and you're starting with your own small company, my suggestion is don't go for the big accounts yet. One, they're not going to give you the time of day, but two, you're not ready for that responsibility because those are accounts with large centrifugals, data center. Like we get into some pretty extreme stuff sometimes, and not that you would know how to find those customers yet. That is something you'll learn as you go. But even if you were to find some of them, it doesn't take much to make a bad mistake, and you're way over your head in liability costs. Okay, so start small. Great places to start with is a lot of these little school districts, especially the smaller ones. They'll not all of them, some of them don't, but many of them, especially in a metro area, will have relatively easy to work on chill water systems. Right, so that would be one example to get into. Now, getting in with a school district is a whole nother political saga in and of itself, but that's an example. Or when you're driving around, many of your strip centers and stuff are going to have, DX based systems with RTUs, but you'll find some that actually have little air cooled chillers sitting around. So like that is your target right there. If you're going to get into that, go find those little small air cools floating around and just go ask to talk to somebody in the facilities team. Just walk through the door or see if they've got a number you can call and just get on the phone with somebody, get in front of somebody, just let them know, hey, I'm here to help. If you need any support, anything like that on your chiller side, let me help you. The reality is most of the big companies, you get it to this point where taking on these small accounts just aren't profitable enough to operate at the scale that we need to. And what that does is it allows for the smaller companies who are trying to get their feet in to pick up those smaller accounts that just genuinely, for the overhead costs of those larger companies, they just can't support. It just financially, it doesn't make any sense. And unless there's a political reason to take on that customer because of some relationship somewhere, it just doesn't make sense. They can't handle that account and still make money. So that's where you have an opportunity as a small company, a smaller contractor who's trying to get into this space. Go find those. They're all over the place. I mean, I'm telling you, you'd be shocked at how many little small hydronic chill water systems there are and how badly they're taken care of, which means how easy it is for you to do a great job. I mean, that would be my recommendation. Um, there's definitely like in the same way that we don't have enough technicians, because we don't have enough technicians to support the chiller side of our industry. Um, we don't. There's not enough company support, because if the companies can't cover all the workload, then that means that there's more work there than there are companies and people to do the work. And you, as a small shop, have a lot of agility because you can very quickly pivot, maneuver, and take care of that customer that that larger shop is going to have a way harder time doing. And that is where you can compete. You can be there when the other guys can't, because there's so much more back end, so much more politics, so much more financial conversations that get into that. How fast can we get there, and why do we need to be there? Is this the right cut? Like, there's if you haven't been on that backside of things, it's hard to really give a clear picture of what that really means. But yeah, you've got opportunity, and that's where I would start. Start with your small air cooled systems, and get involved with them. You're going to get told no a lot, but you'll start to get told yes sometimes, or you'll leave your card with somebody. The guy that's taking care of them makes a mistake, can't get there, whatever. And then you can come in and offer an alternative because they need somebody now. The other guy can't. There's your window. Take it, do a good job. Just one by one, you'll build your reputation, you'll take on accounts, and you'll get more opportunity. That would be my recommendation. Okay. All right, we're going to wrap it up there. I really appreciate everybody's time. If you're not already in Chiller Academy, I'd love to work with you over there. That's chilleracademy.com. I've got a whole suite of options over there to try to help you with your journey. Plenty of free ones, in addition to some paid ones, which this is what I do full time. Okay, this is my full-time job, my gig. This is my retirement as far as I'm concerned. Helping you, building this content, and providing the resource I never had. The resource I really wish I had. Nobody else has built it. Nobody else has taken the responsibility. So I'm trying to now. This is my goal. This is my dream. And this is the mission that I'm on. Our industry needs this. I'm here to help. I'd love to help you as much as I can. And the Academy is my current best way of doing that. With that, MTT, make the time for your family, for your spouse, for your kids. We're in busy season. The time is not going to be there. We have to make that time. And sometimes that might mean we have to say no. We also have to keep in mind we do have to provide. So there is a balance. But if we don't try to make the time, and if we don't try to fight for that balance, and if we always give in to everything, that time is going to slip away. And something that's really become apparent to me with experience and age is the time with them is not replaceable, but the work, it's there. It will figure itself out, and it is there. There is work. And we have the blessing of that in today's environment for us as technicians. But there won't always be the family there. There won't always be the kids. So if we don't make that time now, it's going to get away from us. Anyway, I appreciate your time.